Hello, and thank you for joining me today as we begin our discussion on forces. So for starters, a force is a push or pull in a direction. So this is your definition for a force. Any push or pull in a specified direction is a force. And because it's got a direction, this has both a magnitude, which is our number value, and a direction. So 5 newtons to the right, 4 newtons north, 3 newtons south. All those are forces that have a magnitude and direction. With these forces, scientists have identified 4 fundamental forces that everything you can think of falls under. So any force you can think of would be classified as one of these 4 fundamental forces. So 1 is the force due to gravity, which I believe you're familiar with. 2 is the electromagnetic force. So anytime you touch something, it's the reason you're not falling through your chair, the reason your chair sits on the floor, the reason you can stand on the floor and don't sink into it. That is all the electromagnetic force. We have a strong nuclear force, which holds the nucleus of an atom together, and a weak nuclear force that deals with radioactive decay in an atom. When we talk about nuclear forces, those are only acting over very short distances. So these are forces that are only present in the nucleus of an atom. So extremely short distances we don't see them interact with them directly too much in everyday life. But gravity and our electromagnetic force, things like friction, are something we feel and work with on a daily basis. So again, these 4 fundamental forces vary widely in strength and distance. So your strong nuclear force is the strongest force of all. So this thing that holds the nucleus together, because your nucleus is made of a bunch of protons and neutrons. Remember, your protons have a positive charge and positives want to repel each other. And so because this strong nuclear force, this is what holds those together. So 2 positives can sit by each other because of this force. But they act over an extremely short distance, such as the radius of an atom, of an atomic nucleus. Your electromagnetic forces have a strength about 1/10 or 1/100, the strength of the strong nuclear force. So if the strong nuclear force had a value of 1, your electromagnetic force would be a value of 1/100 or 0.01. So 1/100th of the value for that force. Your gravitational force is something you're familiar with. And we think of gravity as being something really strong. But in reality, compared to our electromagnetic force, we are 10 to the 40th times weaker. Gravity is 10 to the 40th times weaker than even that. Okay, and so that is an extremely weak force comparatively to the other 4 fundamental forces. Not that it's anything to be discredited, but it's nothing compared to those others. Talking about forces that we can see and work with on a daily basis and interact with on a daily basis. For example, if you push a shopping cart, the cart moves, right? You go to the store, you push a cart, the cart moves. If you catch a ball, it's going to stop. These are contact forces. You pushed on the cart then moved. You hit the ball hits your glove, the ball then stopped. These are 2 things coming into contact. Those are called contact forces, which is one classification of force. We also have these things called field forces. So field forces don't have to come in direct contact. They act from a distance. So gravity is a fantastic example of a field force. We don't have to be touching the earth to feel the effects of the earth. We can fall from the sky and you will fall quicker and quicker until you reach the ground, because gravity is a field force. And we can use both these contact and field forces to make an object move or stop moving. So to change motion, we can use either contact forces or field forces. They both work in that regard. They both cause a change in motion. When we talk about these forces, there's 2 terms that we use to describe them. One of those terms is a balanced force, and one of them is an unbalanced force. We're going to talk about this here right now. So suppose you and a friend are going to push this couch. Is it easier to push and move a couch if you're pushing on opposite sides, pushing together, or on the same side, pushing in one direction? Well, if you're going to move a couch, and you want it to be easy, you're going to work together, stay on the same side, push the couch one direction. And so this creates what we call a net force. A net force is the combination of all the forces acting on an object, or in this case, the sofa. And this net force will determine whether or not your object or sofa move. If there is a net force acting on an object, the object not only moves, but accelerates in the direction of the net force. So if it's moving already, it's going to accelerate in that direction. It's going to speed up in that direction. If it's a force opposing it, it's going to slow down. So that's the acceleration piece. We're changing the velocity of the object. If your net force is 0, this will not cause an object to change its motion. So you will have no acceleration. Your object will stay as is, will continue in its state of motion if your net force is 0. And so we'll do some looking at this more as we go through this unit, and we'll talk a little bit more about it today. If we're talking forces, we have these balanced and unbalanced forces. So if you have a balanced forces do not change the motion of objects. So again, balanced force means a net force of 0. You have, for example, you can have an object here, and you can have 5 newtons going this way, and you can have 5 newtons going this way. And because they're in opposite directions, we're going to subtract them. So 5 minus 5 is 0. So my F net, my net force, is equal to 0 newtons, which means my object is not going to change its motion. If it's stationary, it's going to stay stationary. If it's moving, it's going to stay in the same motion. So balanced forces do not change the motion of objects. They cause a net force of 0, which you saw in the diagram above, my little picture, and doesn't cause an object at rest to move. It doesn't change a moving object, cause it slow down or speed up or turn. For example, you have a light fixture hanging from the ceiling. This light fixture is stuck. It's suspended. It doesn't move up and down, doesn't move side to side, because the tension in the cord is equal to your force balances let's undo those. Tension in the cord balances the force of gravity pulling down. So you have gravity pulling this way, you have a cord pulling this way. These are the same forces, so the net force is going to be 0. Unbalanced forces. These are different forces. So we had 5 and 5 up here. If I change one of them, and if instead I would make this a force of 10 newtons. Let's draw here. If I make this a force of 10 newtons, I have unbalanced forces. They don't completely cancel each other out. So suppose 2 students on one side of an object and 1 student on the other. So we have 2 students here pulling versus 1 student pulling here. So if everybody pulls with a force of 5 newtons, because I have 2, I have 10 newtons on this side and 5 on this side, which is going to give me a net force. My F net is going to equal 10 newtons minus 5 newtons, which equals 5 newtons. And we said forces need a direction, so this is going to be newtons to the left. So that's going to be my net force on the object. And because it's got a net force, it's going to accelerate in that direction. And so because there's a net force, the object will move, and not only move, it will accelerate in that direction. If the forces are in different directions, so for example, if I had a different box, and I have one person putting a force here of 5 newtons, and I have one pushing here with 5 newtons, this object is going to end up going somewhere in this general direction. It's a combination of the two. For example, if we have a force coming from the north and the east, I have mine coming from the west towards the east, it would go in the northeast, in this case, the pushing towards the north. So this is coming from the north. So pushing south and pushing west, this one's going to be towards the southwest direction. That's going to be my direction on my net force. One of the forces you're familiar with that we use a lot and we deal with a lot in life is friction. So imagine you have a car rolling on a flat, even surface. So on a straight road, you let off the brake and you coast. Because you've been in a car that you left the gas before, sorry, gas, not the brake. You left the gas and you slow down. So because you've done that before, you've ridden a bike and you've quit pedaling and you eventually slow down, you have experience that says you're going to slow down until you eventually stop. And because there's a steady change in motion, we have to have some sort of force acting on our object. In this case, the force must be friction. So friction is, so your vocab term here, friction is a force that opposes motion between two surfaces that are in contact. So friction doesn't act from a distance. It's not a field force. This is a contact force. Example over here, we have a match being struck. So the reason you can light a match, the reason sparks fly is because of this contact right there. So friction occurs because the surface of any object is rough and the friction creates heat. So we have rough surfaces create more friction than smooth surfaces. But even if a surface looks smooth, it will still have these little microscopic hills. If you saw it under a very high-powered microscope, you see these little grooves, little hills. This allows for friction. So there's always going to be some sort of friction. Just in some cases, there's more than others. When we talk friction, there's two different kinds. If you've ever pushed an object before, you've noticed that it's harder to start something moving than it is to keep it moving. So the starting friction we call static friction. Static being a force that resists the initiation of sliding motion. So the force of an object, or the friction of an object at rest, is static friction. So this is the friction between two surfaces that are stationary. And this is always greater than, I'm going to call it Fs. Static friction is always greater than your F of K, or your kinetic friction. So there's kinetic and there's static. So static friction is between objects at rest. Kinetic friction is a force that opposes the movement of two objects that are in contact and sliding past one another. For example, you push a box across the floor. You move a chair across the floor. You slide your feet. You drag somebody. All of those are kinetic frictions that you're dragging. You're moving one object across another surface, and that has friction between them. So static was friction between stationary objects. Kinetic friction is friction between moving surfaces. And then the force for stationary objects to start moving is always greater. It's always greater, or it can be equal to, but 9.5 times out of 10 it's going to be greater than. It's usually greater. At worst, it's equal to. You will never have kinetic friction. Kinetic friction can never be greater than static friction. It can never take more energy to keep something moving than to start it moving. If that were the case, you'd quit moving it each time. You'd push and stop, and it would get really annoying, to be quite honest with you. But that is friction. So we have different kinds of friction. So we have different kinds of kinetic friction. So because things are moving, things can move in different ways. So if objects are sliding past one another, we have what's called sliding friction. Very scientific, super complex term. So a box sliding across a floor is going to experience sliding friction. We also have, so one of the ways we can reduce the friction and make things easier to move is we can put wheels on them. So if you have an object on wheels, this is where dolly carts and things of that nature come in. Wheels make things way easier to move. This is because we have rolling friction. And remember, friction is a contact force. It can only occur between two surfaces that are in direct contact. So if you look at this box, I have all of this surface here that's in contact with the ground, which creates a lot of friction. On these, I have just this tiny little bit of wheel right here is in contact with the ground. The rest of it is not. So there's a very small amount of friction to overcome. I just have to push enough to get this next little piece rolling, and then we're going to talk inertia and what that means, and that helps a lot too. Rolling friction is usually less than sliding friction. I'm going to go out on a limb and say it's always less. I can't imagine too many cases where the same object with wheels is going to be harder to push than without wheels. But we'll say it's usually almost always less. Sometimes we need, so friction in some cases can be very bad, very detrimental. Other times we need it. So friction is necessary for many everyday tasks to work correctly. For example, you drive your car. Your car works because of friction. You walk. The reason you can walk on concrete much easier than ice is because there's friction. So imagine walking on ice everywhere. Would be quite terrible. You'd have to take objects and throw them so you can slide to where you're trying to get to. You run out of things to throw and you might hit somebody while you're throwing or get hit. Neither one's good. We can have unwanted friction. We can lower it. So if we don't want friction to be there, we can lower it using materials such as oil, wax, and grease. So we oil things like hinges. You wax surfaces that you want to be smooth and slick and not have friction. All of these are non-stick coatings that reduce the amount of friction that objects experience, which are ways that we counteract that. If we're talking motion and we need friction, we can also increase it. So for example, helpful friction can be increased. So we can increase the friction between two surfaces, such as putting sand on icy roads, wearing batting gloves when you play baseball or softball. All of those are helpful forms of friction. Your shoes, when you play sports or basketball or even walk, you want friction there so that you can turn and move and run and not slip. So all of that's helpful friction. And the other way you can increase your friction is to increase the force pushing the surfaces together. So heavier objects produce more friction than lighter objects. If I have a box that weighs 100 kilograms and I have another box that weighs 10 kilograms, my 100 kilogram box is going to have more friction because there's more force pulling it down. It weighs more, so it's going to be harder to move. There's more friction. So the added mass increases the friction between your surfaces. That is one way that we can use a helpful form of friction. Again, we talked a little bit about cars. Cars only work because of friction. So tires in the road come in contact. There's friction between them. The tires push one way, the road pushes the other, which allows the car to move. This is an example. You have an unbalanced force. So there's a greater force going forward than there is going backwards, so your car is going to accelerate. In this case, the forces are equal, so this car is going to move at a constant speed. And you can even have balanced forces on a hill. So if you park your car on a hill, you're going to have balanced forces there that go forward and backward the same amount. And so your brakes work. That's a fantastic example of friction. The reason you're allowed to stop is because of friction, which is a great use for it. So without brakes, we wouldn't be able to oppose the car's motion to slow down or stop. You'd be going non-speed or faster the whole way, which wouldn't end up well for you. And last but not least, like I said, it can keep a car stopped on a hill even, because there is that opposite motion. So that is friction. That's looking at forces. A couple review questions for you quick. I would like you to identify the fundamental forces in nature. I want 2 of them. I want you to be able to name 2 of those. Give me an example of an unbalanced force acting on an object, and then I want you to explain why friction is important with driving a car. Thank you very much for your time and attention, and I will see you next time.